Beth.
And I'm Beth.
Welcome to Physics with Beth and Beth. Hello and welcome to Physics with Beth and Beth. I'm Beth. We're on this AP Physics C mechanics curriculum, also your engineering physics curriculum. In college, Unit 2, Newton's Laws of Motion, also known as dynamics. And we have a problem. We have had a series of problems using Newton's second law with blocks on a plane, flat plane, then on a ramp, then interacting with a wire or pulley system, and then even on a ramp interacting. Now we're going to be doing this hanging sign problem. It's a problem that the AP board loves as well as college professors because it really demonstrates a high level of understanding of Newton's second law and free body diagrams. So we're going to get started. I have a sign hanging from two wires. This is going to be called, and instead of doing, I know we can do these interchangeably. Force of tension, it means the same thing as tension. All right, I'm just going to do T here, and that way we get used to seeing all of them. But I've got tension 1 here, and I have tension 2 here. Okay, and these three wires are not even. And you know that because angle, we got an angle here of 53, we got an angle of 37 here. So they are not the same length, those two wires. We also have a sign, 0.5 kilograms hanging from it. Where would you see something like this? Maybe if you go to historical downtown, you've got all the cute little shops in your historic downtown, and you look up and you see the signs hanging from two wires saying the name of the store. It's a classic place to find these. All right, I've already done the free body diagram because we've been doing free body diagrams. We now know what this looks like. We have two wires, so we have a tension. I'm just going to call this tension 1, and I'm going to call this tension 2. All right, we also have that sign has mass of 0.5 kilograms, so we have weight or force due to gravity down, which is equal to mg. They're going to ask you, hey, tell me what the tension in wire 1 is and what is the tension in wire 2. Okay, so here we go. We're going to sum forces in the x and the y direction, or the horizontal and the vertical direction. I'm going to go ahead and draw a line here so you can see this. This tension 1 and tension 2, part of it's in the horizontal direction, part's in the vertical direction. This is northwest, so it has a north component and a west component. T2 is northeast. So it has a north component and it has an east component. So I'm going to draw these components. Here is my tension 2 in the x. Here is my tension 1 in the x. And then I have my vertical component. This is T2 in the y. And this is T1 in the y. All right, now I'm also going to talk about these angles. These are parallel lines with the line bisecting it here. So if that's 53 degrees, that means this is 53 degrees. And if that's 37, it means this is 37 degrees. Just so we get our angles straight. We're going to get started. We're going to sum our forces horizontal and then in the vertical, knowing that this sign is not moving at all. So my acceleration in both directions is 0, which means my two horizontal forces have to balance each other. I know it doesn't look like that, but they do. And then my two vertical forces minus my force due to gravity have to balance each other. So here we go. I have tension 1 in the x direction, and that's west, so it's negative, plus tension 2 in the x, which is east, is positive, is equal to 0. I'm going to solve. I'm just going to add my tension 1 in the x over, and I have this. Now remember, all of these are forces, they're vectors. I'm just not going to take time to write all of my arrows and waste your time while I draw all those. Okay, now I would like these two horizontal components in terms of the whole tension, the hypotenuse. Okay, how can I do that? Well, with SOHCAHTOA, our best friend, all right, this tension 1 in the x is adjacent to this angle. It's adjacent, so that is cosine is adjacent over hypotenuse, right? SOHCAHTOA. So I'm going to do that over here so you can see it, that I have my cosine 53 equals my adjacent side, which is that tension 1 in the x, over my total tension of that hypotenuse. I multiply that over, and I get that my tension 1 in the horizontal component of it is T1 cosine 53. So I'm going to write that in here, T1 cosine of 53. All right, now I'm going to do the same thing for my tension 2 in the x. That's going to be cosine, it's adjacent to that angle 37. That's going to be this tension 2 horizontal component divided by my total tension 2 of that hypotenuse, multiply that, and we get that my tension 2 in the x is my total tension times cosine of 37. All right, perfect. Now, I have two variables here, and I can't solve for either one with two variables that I don't know. And I'm looking for what is my tension force 1 and my tension force, my force of tension 2 and my force of tension of 1. So I'm going to go, well, I can't do anything with that. I'm going to go sum my forces in the y and see what happens. All right, so I've got my tension 2 in the y that is north, so it's positive. I also have my tension 1 in the y, which is also north and positive, minus my force due to gravity, which is down, equals 0, because again, no acceleration in the vertical direction either, because this thing's at rest. I'm going to need these two expressions in terms of T1 and T2. So here we go. T2 in the y, that is opposite that angle, so that's sine. So it would be sine of 37 equals my opposite, which is that tension force in the y divided by my total tension 2. Multiply that, and you now have an expression for that tension 2 vertical component. So I'm going to plug that in here. Okay, because we're getting the hang of this, hopefully we've already had the hang of it, we'll know that T1 is opposite, it's sine of 53. So it's going to be T1 sine of 53, and my force due to gravity is mg. All right, now I have two variables again that I don't know, and I can't solve for either one of these when there's two variables in the same equation I don't know. But what if I solve for T1 and I plugged it in right here? Then I would only have my tension 2 in the problem. So I'm going to do that. I have T2 cosine 37 divided by cosine of 53 equals tension 1. And that's the whole hypotenuse. Oh, that's the whole hypotenuse too. So I'm going to take this whole expression and plug it in here. Nobody said this was going to be pretty. All right, we have T2 sine 37 plus I have T2 cosine of 37 divided by cosine of 53. But here's where a lot of students, they're rushing through a test and they're like, okay, yeah, I know to plug that in. T2 cosine 37 over cosine 53. However, they forget there's still a sine 53 here. So there's still another sine 53 here. Minus mass is mg. And I'm actually going to go ahead and add that over mg at this point. Okay, look, I only have tension 2, the hypotenuse. That's all I have left in this. I know mass is 0.5 and that's 9.81, and I can solve this thing. T2, this sine of 37 is 0.6018 T2 plus, if I take cosine 37 times sine of 53 divided by cosine of 53, I get 1.06 tension 2. So cosine of 37 times sine of 53 divided by cosine of 53 is how you get that number, equals my mass, which is 0.5 times 9.81. All right, I'm going to add these. These are like terms, and I'm going to get 1.6618 T2 equals 4.905. Now I just divide both sides by 1.6618, and my T2 equals 2.95 newtons. And I have tension 2. Now I need tension 1 though. They asked for both. Well, okay, hey, I've got an equation for that right here with T2 in it. I know T2 now. So that's going to be 2.95, which is T2, times cosine of 37 divided by cosine of 53, and I get T1, which happens to be 3.91 newtons. And that is how you do this problem. It's not pretty. This gets pretty ugly right here. But that is how you do that tension. And my tension 1 has more force than my tension 2, if you notice that. Okay, perfect. Hope that helps. Hope you understood that. And thank you for watching. If you haven't subscribed, we'd love for you to subscribe. And if you want to share, if this video is helping you and you want to share with your peers in class, we would love that as well. But thank you again for watching, and happy physicsing.